Hi, this is my video number 14 for differential equation. In this video I'll talk on the nonlinear system. For this video I think I got a better phone holder, so my video should be much better. Now, so we consider the nonlinear system. What is nonlinear system? So we have let's consider that system, this system x, a function of xy, where this is equal to ax plus by plus epsilon 1 of x and y, and y dot, let's say this is qxy, this is equal to cx plus dy plus epsilon 2 xy. All right, and then we assume that the pq and the partial derivative are continuous. P and q and the partial derivatives are continuous in some neighborhood of the critical point not. Derivative, partial derivative means we have del p del x, del p del y, as well as del q del x, del q del y. This is continuous. And the number 2 is that AD minus BC is different than 0. And if you have number 3, the limit r goes to 0, epsilon I xy over r, that equal to 0 for I 1, 2, where our r is x squared plus y squared. Now, if this is the case, then we say 0, 0 is a critical point. In this case, this implies that 0, 0 is a critical point of our equation. So this equation, let's give a name there. Let's call this number 1 of 1. Okay, so if the system 1 satisfies these 3 conditions, if 1 satisfying those conditions 1, 2 and 3, then we say 0, 0 is a simple critical point. Simple critical point. Okay, so now in the previous video we have dealt with linear system where we don't have epsilon 1, epsilon 2, right? Now we deal with the nonlinear system. In this case, involve epsilon 1, epsilon 2, and we'll show that to you that this system behave as like the linear system. Okay, so now let's consider. So we let C the trajectories, x, xt, y, yt be the trajectories of trajectories of our system 1, then we can represent that, then in polar coordinate we can have C, we can represent C as R, a function of t. This is obvious because X a function of t, Y is a function of t, and R is a function of xy, means R is also a function of t. And we have W as also function of t, where RT is positive, where X is R of t cos omega t, and Y is RT sine omega t. Oh, this is the problem with this, not enough space. Okay, now I will define the condition where we have a spiral point, we have a knot point, we have a proper knot, and so on. The definition, we assume that there is a neighborhood U, there is a neighborhood U of a simple critical point, The simple critical point must satisfy the three conditions given above. 0, 0 of our system, non-linear system 1, in which we have the trajectory are defined. All the trajectories are defined in t0 t infinity, or we may consider minus infinity to t0 for all t0. And number 2, the limit of RT as t goes to infinity equal to 0, or limit of RT t goes to negative infinity, that's 0. Then we have 0, 0 is set. We have first case is a spiral knot. A spiral knot. If the limit of omega t or wt t goes to minus infinity, we need absolute there, this equal to infinity, or we take limit t goes to infinity, omega t that goes to infinity. For all trajectories in U. Remember that U is the neighborhood of our point x0 at naught. So in this case, it means that if we have let's say this is our critical point, this is the neighborhood of the U. Alright, so all trajectories here, as t goes to minus infinity or t goes to infinity, it goes out of that, getting out. So it goes to infinity. So in this case, we call it as a spiral net, spiral knots. Number 2, we have a knot. Yeah, a knot. If limit t goes to infinity, absolute of omega t is equal to some constant c, yeah, or limit t goes to negative infinity of omega t that equal to c. For c constant, yeah, for all the trajectories, all trajectories in the neighborhood of x naught, neighborhood of naught naught. Yeah. And c, we have a proper knot. If it is a knot, and for every constant c, and for every constant c, there is a trajectory, and there is a trajectory satisfying limit t approaches infinity omega t equal to c, or limit t goes to minus infinity equal to c. Okay, so we have 3 cases here. We have a spiral knot, we have a knot, and we have a proper knot. With that, all those conditions, I will provide example for this. Let me explain first, and let me give you some notes. Definition, we have another definition. A simple critical point. The simple critical point. Simple critical point 0, 0 of 1. Yeah, this is the nonlinear system, is said to be center if there exists a neighborhood of naught naught containing countably many closed trajectory. Many trajectory, each containing naught naught and whose diameter tend to 0. Each containing naught naught and whose diameter tend to 0. So what does it mean? So it means that if you have let's say this is our plane, then this is we call it as a center. Yeah, direction is depend on c. Yeah, either is clockwise or counterclockwise. So that's we call it as a center. If you can consider there is a neighborhood not containing, so means that if you have a, let's say this is the we have, let's say this is our u, let's say the neighborhood of x naught y naught, then we have countably many closed trajectories which contain the critical point not there. This is the critical point in the middle. And we have B, we say a saddle point. If there are two trajectories two trajectories approaching 0, 0, approaching the critical point 0, 0 along opposite direction. Opposite direction, and all other direction close to or either of them, and tend away to from 0, 0. Opposite direction and all other trajectories close to either of them and to 0, 0. Tend away to infinity. Tend away from them as t tend to infinity. So this is, we call it as a saddle point. So we have two trajectories approaching 0, 0 along opposite direction. So we have, in that case, so we have that opposite direction approaching not, whereas others away from that. So others away from that. So we have something like that. So this is, we call it as a saddle point. So you can check the direction of this. There goes at the same direction. For this, it goes towards the 0, but then it's divert to the infinity as well as this. And for this, from y it goes to x to the infinity, and this from y goes to x negative infinity. So this is the spiral knot. Okay, and we have for the proper knot, as I mentioned earlier in the previous definition, I've given the center, and for the spiral knots. So this is the spiral knot. All right, it either goes inside or goes outside. I mean, either close to the 0, 0, approaching 0, 0, or away from 0, 0. It depends on the definition of it depends on our problem. A spiral knot. Then we have a proper knot. This is the proper knot. So you can have as many as those. That's proper knots. And we have, this is proper knot, proper knot. Okay, and we also have a knot. Knot go through the critical point, knots. So we have something like that. We have something like that. We have that. So this is a knot. Okay, and we have improper knots. For the case of improper knot, we have that. So it goes that, and some goes like that. This is improper knot. Okay, now I'm going to state without proof a theorem describing how the trajectories of our nonlinear system that I given in the beginning of my video with a certain condition are related to the linear system that we have discussed earlier. So near the simple critical point. So means that from the system that we have, the nonlinear system, we have x equal to ax plus by plus epsilon y xy, y dot is equal to cx plus dy plus epsilon 2 xy, and we want to see the relationship between this nonlinear system and the linear system ax plus by and y dot is cx plus dy. So basically what we can do, especially near the we want to see the trajectories, the behavior of trajectories near the simple critical points not known. Okay, so we call this as a Poincare theorem. Yeah, Poincare theorem. Can you see this? Oh, sorry about this. Okay then. So we have this nonlinear system, and this is the linear system, and we want to see the trajectories near the simple critical point not knots. Okay. Okay. Now I give you the theorem that I mentioned. Theorem. If 0, 0 is a spiral point of the linear system, I put it that LS linear system, then it is a spiral, then it is a spiral point points of the nonlinear system. Okay, and number 2, if not knot is a knot of the linear system, then it is a knot for or of the nonlinear system. Okay, and number 3, we have if not knot is a saddle point of linear system, then it is a saddle point of nonlinear system. And number 4, we have if 0, 0 is a proper knot of linear system, and then it is not necessary a proper knot of nonlinear system. However, if we give a further restriction to the nonlinear part, the epsilon. Yeah. For example, if you have epsilon, we take a limit. R goes to 0 of epsilon I R 1 plus alpha. That one is bounded. If that is bounded for some alpha positive, then 0, 0 is a proper node. Proper node of the nonlinear system. And we have number 5. If 0, 0 is a center of the linear system, so it is either a center or a spiral point of the nonlinear system. Okay, so this so we call this as a Poincare theorem, yeah, due to Poincare, 1800 something, yeah, Poincare theorem. So in this case, if the elliptical characteristic of the linear system is sufficiently distorted by epsilon, by our nonlinear part, then to make them spiral. So if you analyze further of this, yeah, or find the RDT, we often got the solution. Okay, so let me give you the example. Yeah, let me give you example. So we have example. Now consider the motion of the pendulum. Motion of a simple pendulum. Yeah. So which is given by theta double dot plus 2k theta dot plus q sine theta that equal to 0 for k positive and q positive. Now we can reduce this to the autonomous system or non-autonomous system. I mean to the autonomous system with the nonlinear autonomous system, where just substitute, let's say x, we substitute x equal to theta, and so x dot equal to y. Yeah, so we have what we have theta, so here is so x dot equal to sorry, I think this is x dot equal to y, sorry. So if we substitute x dot equal to y, yeah, x dot equal to y, so what we have, so that x dot equal to y, so this we have here is x dot and y, I think y is equal to theta, is it? No, let's try that. Y equal to theta, then we have y dot is equal to theta dot, no, this is something wrong here. Yeah, what times now? I think I'm running out of time, so I stop here. Then I'll give you in the next video. Okay, I'll cover this part in the next video. Okay, I stop here. Before that, let me conclude what I have given in this video. We are dealing with the nonlinear system, and all the definition and the theorem that I given, the definition is to identify the form or the path of the trajectory. Yeah, either its center is the spiral a node, yeah. And also we have a theorem to relate the what we call this trajectory near the simple critical point of the nonlinear system as well as the linear system. So there is a relationship between linear system and nonlinear system. Alright, so with that I stop here for this video, and I will give you an example in my next video. Bye.